significant figures, when you go to the lab, what do? You take the rulers, you place the rulers on a table, for example, to measure the length. Now you're going to keep collecting the digit until you find the last reliable digit. That's the significant figures. Last reliable number. What is last reliable number? Last reliable number can also be said as first uncertain number. Uncertainty can be calculated as half the last reliable number. You divide the last reliable number by half. That's the uncertainty. Okay, so for example, if this is the number come from your measurement 0.60123 meter, what is the last reliable number? Last reliable number definitely not 4, definitely not 3. Last reliable number is 2. Why is that? Because human eye only can see 100 micrometer, which is 0.1 millimeter. Okay, beyond that human eye cannot see. It does look blurry. So there is no problem with 6, there is no problem with 0, there is no problem with 1. There is a problem with 2 because it's the last reliable number. So 2 is the problem you are not 100% sure about. So 2 is where you have to take care of the business. Okay, so how do you gonna write? You're gonna write half. Last reliable number, should we write 2? Absolutely not. We should not write 2. What should we write? We should write 0.000. Should we write 2? Absolutely not. We should write 1. Why is that? Because we want to write in terms of place value, not in terms of number itself. The place value. Is this 10th place? No. Is this 100th place? No. Is this 1,000 place? No. Is this 10,000 place? Yes. So that's what we need to write. Okay. So let me explain why 2 is not. 2 is the last reliable number and why not 3 and why not 4. Okay. Let me erase this. All right. So what are you going to do? You're going to write 0.60123 meter. Okay. So let's write 6. 6 what? Decimeter. 6 decimeter is equal to 0.6 meter. Let's write 0. 0 centimeter is equal to 0.00 meter. Let's then write 1 millimeter, which is 0.001 meter. Let's write 200 micrometer. Why it is 200 micrometer? 0.0002 meter. Why 0.0002 meter is 200 micrometer? It's because 0.0002 meter times we need the micrometer, which is on the top, meter is on the bottom. 1 micrometer is 10 raised to negative 6 meters. Okay, so meter cancel. Scientific notation of this one is 2 times 10 raised to negative 4 divided by 10 raised to negative 6 micrometer. So 2 times 10 raised to negative 4 positive 6. Therefore, it is 200 micrometers. Okay, now you're going to write 330 micrometer is equal to 0.00003 meters. Finally, the last one, 4 micrometer is equal to 0.00004 meters. Now, which measurement? There are how many measurements? 1, 2, 3, 4, 5, 6. All measurement wasn't done by the same student. The first measurement was done by what? The first measurement, okay, so let's say, no, let's not talk about that. Let's talk about in a separate problem. Okay, so this is what it is. Now, human eyes do not have access to anything beyond 200, anything beyond 100 micrometer. So 200 micrometer, yes, good. All right, so this is probably done by microscope. This is probably done by microscope, not by human eyes only. And human eyes, of course, can do better than this. Can do better. Okay, so this is the acceptable one. So how can we write this? We can write this as 0.000. Oh, no, we're going to write this as 0.6012 meter plus minus. Okay, then we have to write the uncertainty. Okay, uncertainty is 0.000000, okay, 1 divided by 2, so 0.5 meters. Okay, so now let me give you three problems for you to solve, and you want to pause, and then you want to solve, and then you're going to resume the video again. The first problem is M is between 15 to 25. Then measurement is between let's say 0.205, 0.195. The last one is 2005, 1995 decimal. Okay, so what is the M? The representative M. What is the representative M over here? What is the representative M over here? What is the representative M over here? The representative means that the number that represent all other possible numbers. Okay, M could be anything between 0.15 to 0.25, but what is the representative M in this case? Okay, so all right, let's do it. So you can use the arithmetic mean. Arithmetic mean is 0.25 plus 0.15 divided by 2, and that 0.40 divided by 2, and that is 0.2. So this is 0.2. What is this one? 0.20. What is this one? 0.200. These are the representative mean. So the measurement lies, okay? So 0.2 is between 0.15 and 0.25. 0.20 is between 0.195 and 0.205, and so on. Now let me give you some examples of sig fig. I'm going to give you the rules of sig fig and then examples of sig fig. Okay, rules of sig fig. Rules of sig fig. Rule number 1. Whole number always sig fig. Always sig fig. So how many sig fig here? 3, 5, 4, 2. 4 sig fig. Number 2, 0 in the middle, always sig fig. 2002. How many sig fig? 4. Or 2001. How many sig fig? 5. Number 3. Leading 0. Never sig fig. 0.002. 1 sig fig. Number 4. Trailing 0. Sig fig. 203. Now let's make some extreme case. Okay, so extreme case would be this one. Number 4.1, I'm going to make 0.2 meter. 4.2, I'm going to make 0.20 meter. 4.3, I'm going to make 0.200 meter. 4.4, I'm going to make 0.2000 meter. And then 4.5, I'm going to make 0.20000 meter. And last one, 4.6, I'm going to make 0.20000 meter. Now, if I write the measurement, so here you have 1 sig fig, 2 sig fig, 3 sig fig, 4 sig fig, 5 sig fig, and 6 sig fig. Now, if I do write the measurement and the list and the list, the last reliable number, and then the uncertainty. The first one is 0.2. Okay, the last reliable number is 0.1. Definitely is not 0.2. Understand that this is 10th place. Uncertainty is, of course, divide by 2, 0.05. But don't forget plus minus because this lies between 0.15 and 0.25. Number 2, 0.20. Okay, it's not point. It's not point something. It's 0.01. 10th decimal place. Plus minus 0.005. Number 3, 0.200, 0.001, plus minus 0.0005. Number 4, 0.200, 0.0001, plus minus 0.00005. Number 5, 0.20000, 0.00001, plus minus 0.00005. Last one, 0.20000, 0.00001, plus minus 0.00005. Now, this one was done by 10 centimeter ruler. This measurement was done by centimeter ruler. This measurement was done by millimeter ruler. This is human limit. This was done by microscope. This one done by electron microscope. Electron microscope. Regular microscope can make the things 1,000 times bigger. However, electron microscope can make the things 1 million times bigger, 1 million x. Okay, so now this is the one we care about. So this is the one you have to write on the lab report. How are you going to write it? You're going to write 0.2000 meter plus minus 0.01234 5 meter. That's it. Good. I'm going to give you one more example similar to this one. So you get the hang of it. Measurement is 0.2. Last reliable number is 0.1, 0.05, plus minus. Measurement is 0.21. Last reliable number is 0.01, plus minus 0.005. Measurement is 0.212, 0.001, plus minus 0.0005. Last one, 0.2123, 0.0001, plus minus 0.00005. Hopefully you get it. Hopefully you get it. Now, you're going to go to the next rule, and that is addition and subtraction, multiplication and division rule of second. So addition and subtraction rule. Addition and subtraction rule. Let's start with an example. 3.1 plus 3.12 plus 3.123. Okay, so what is that? Our calculator gives us 3.1 plus 3.12 plus 3.123, and that is 9.343. Now I'm going to give you the rules. Final answer can be more precise than the number with least precise. Then the measurement with least precise. Measurement with least precise. Okay. All right. Final answer can be more precise than the measurement with least precise. Okay, good. So, let me see. Did I? Yeah. Okay. Least precise. So which one is the least precise? This one is the least precise. Least precise one has how many decimal? Only one decimal. So final answer cannot have more than one decimal. So the final answer is 9.3. Okay, now let's do the subtraction. Do the subtraction. We're going to do 10 minus 3.1, 100 minus 3.1, 1000 minus 3.1, 10 minus 3.1, 6.9, 100 minus 3.1, 96.9, minus 3.1, 996.9. Okay, here this is the least precise one. Least precise one has one decimal, zero decimal. So this cannot have any decimal. This has to have zero decimal. So I have two options, 6 or 7. It has to be 7 because 6.9 is close to 7, then close to 6. All right. This one has zero decimal. Final answer cannot have any decimal. Okay. So the final answer, 96.9, is close to 97, then 96. This one has no decimal, so this one cannot have any decimal. So 996.9 is close to 997. So this is the addition and subtraction rule. Now let's see division and multiplication rule. So division and multiplication rule. So let's say 3.1 times 3.12 times 3.123. How much? 3.1 times 3.12 times 3.123, and that is 30.205656. Let's write down the rules. Final answer can't have more sig fig than then the measurement with least sig fig. Which measurement has least sig fig? This one has least sig fig too. Final answer cannot have more than 2 sig fig. So it's just 30. All right, let's do division. 10 divided by 3.1. 10.0 divided by 3.1. 2. Number 3. 10.00 divided by 3.123. So let's see what calculator give us. 10 divided by 3.1, that is 3.225806. 10 divided by 3.12, and that is 3.205128. 10 divided by 3.123, and that is 3.202049. Now here, how many sig fig I have? Here is 2 sig fig, here is 2 sig fig. Final answer cannot have more than 2 sig fig. So 3.2 is the final answer. Here I have 3 sig fig, here I have 3 sig fig. Final answer cannot have more than 3 sig fig. So 3.21. This is 5, I'm rounding it to nearest. This one has 4 sig fig, this one has 4 sig fig. Final answer cannot have more than 4 sig fig. So 1, 2, 3, 4. I check the last digit, which is 0, less than 5, so we keep it as it is, 3.202. Okay, so that has been the sig fig.